Machine learning traditionally relies on massive scale, but deploying AI at the absolute edge requires microcontrollers to operate on sub-milliwatt power budgets. Many edge deployments begin with hardware like the Raspberry Pi, relying on its central processor to manage the workload. Moving down the hardware stack to boards like the Arduino, available resources drop from gigabytes of memory to systems constrained by dozens of kilobytes. Recent research has validated 20 frame per second visual anomaly detection on 5.41 megabytes of memory and acoustic tracking on as little as 30.5 kilobytes. These efficiencies stand in stark contrast to standard machine learning, which allocates dozens of gigabytes of VRAM just to process a single data stream. Because the physical limitations of a microcontroller are fixed, engineers cannot simply shrink a standard neural network. They must rebuild the mathematical operations of the network itself. Supervised learning defaults to a requirement for balanced datasets, training a model by comparing healthy operations against thousands of examples of specific, catastrophic defects. This funnel maps the primary failure point for industrial edge and AI, the data bottleneck. Collecting comprehensive failure data is often a logical impossibility. To map every defect, an industrial system would have to experience repeated, expensive breakdowns that a reliable facility is designed to prevent. Real-world conditions make acquiring defect data unfeasible. For TinyML to survive, it must move away from the supervised learning model entirely. Fitting neural networks into embedded memory requires strict hardware separation. Static weights are stored in flash, while volatile calculations cross into the SRAM. This limited space, the tensor arena, is the active workshop where the network unpacks feature maps during live inference. Standard floating point models are physically too large to cross into this arena. To fit, parameters must undergo post-training quantization, crushing them down to int8 integers. This formula maps the direct mathematical translation used in the quantization process. The system takes the real input value, divides it by a calibrated scale, and adds a 0-point bias. This forces heavy floating point data into an ultra-compact integer space. Quantization is the mathematical bridge that allows infinite theoretical numbers to operate within the finite constraints of physical silicon. To solve the lack of defect data, researchers utilize normal-only learning, implemented in computer vision through the self-supervised tiny glass framework. The process begins by stripping away the massive wide ResNet 50 backbone, common in large-scale vision, replacing it with a lightweight ResNet 18 model. The network trains exclusively on healthy images. To understand failure, it artificially synthesizes its own defects, projecting rough textures onto normal images to distinguish anomalies. During inference, the model runs a dual evaluation. First, a global anomaly score detects broad image-wide deviations. Simultaneously, it calculates a local anomaly score, isolating microscopic irregularities down to specific patches in the visual field. By hallucinating failure states, an 8-megabyte camera performs accurate quality assurance at 20 frames per second without relying on historical defect logs. Beyond vision, edge networks must also parse high-frequency acoustic signals and structural vibrations to monitor the health of industrial machinery. The EPC TinyAD framework manages this through a technique known as teacher-student knowledge distillation. A massive teacher autoencoder learns the normal soundscape, transferring its deep understanding into a tiny student network. To sharpen its logic, engineers hide random segments of the acoustic signal, forcing the tiny model to mathematically reconstruct the hidden data. This distillation allows a microscopic chip to inherit the structural insights of a massive neural network, enabling it to identify mechanical shifts with minimal power. Some deployments occur in entirely new environments, where no prior data, healthy or otherwise, exists. This requires a cold start. Deep learning cannot function without an initial baseline. In these cases, the system must pivot to statistical on-device learning. This is the role of the Yosei-Ue algorithm. It utilizes a treep, a randomized structure that merges the properties of a decision tree and a heap. Yosei-Ue uses mass-driven priority logic. It detects the density of incoming data, isolating the rarest, most anomalous points and trapping them near the root of the tree for immediate detection. This approach cuts training time by 126 times and reduces latency 7-fold compared to standard isolation forests. At the extreme edge, algorithmic efficiency dictates survival. Where neural networks lack the data to start, elegant statistical sorting provides the solution. By utilizing normal-only learning and intense mathematical compression, engineers reclaim critical kilobyte space within the tensor arena. This overhead allows microcontrollers to handle sophisticated data types, such as 60 GHz millimeter wave radar for privacy-preserving human tracking. A single chip can now fuse low-resolution time-of-flight sensors with infrared thermal arrays to analyze complex human behaviors. These same acoustic models are expanding into high-frequency ultrasonic guided waves, mapping material damage in structures in real time. Software compression provides the necessary overhead for basic embedded chips to perceive the world through high-frequency multimodal spectrums. The ultimate result of this efficiency is the transition to self-powered sensing. Devices can harvest energy from the vibrations of the very machines they monitor, using those same mechanical pulses as the primary data source for the onboard TinyML model. TinyML is a ground-up reconstruction of AI, a shift from centralized, data-hungry servers to billions of self-sustaining nodes woven directly into the physical world.